this video, I wanted to review the content from Chapter 3, which we did in live class, but I didn't post any videos. And I know a few of you are a little bit behind or lost on it, so I just wanted to look over this example. So, like for example, the SAT scores from these high school students follows roughly a normal distribution with a mean of 1060 and a standard deviation of 200. And its first thing it asks us to do is use the density curve to determine the central interval, which contains approximately 95% of the scores. But using the 68, 95, 99.7 rule, we know that 68% of scores, I don't know what's happening, sorry. That 68% of scores, it's because I didn't lock this. 68% of scores fall within one standard deviation of the mean, and 95% of scores fall within 2 standard deviations of the mean. So in this case, our mean is 1060. Our standard deviation is 200 of our population. And we would want to do mu plus 2 sigma and mu minus 2 sigma to find to find the interval which contains 95% of the scores. And this is not to be confused with confidence intervals. That's when we're talking about sample data when we have a sample size. Here we're assuming this is for the entire population. Very similar, but actually a little bit simpler. But anyways, if twice the standard deviation would be 400, so this would give us a range of 1060 plus 400, which is 1460. And 1060 minus 400, which is 660. And this would be a central interval which contains 95% of the scores. We can kind of visualize that by looking at it right about here. And that should give us about 95% of the data based on the density curve, that is. Now, again, it won't necessarily fit the exact data, but yeah. So the next question asks us, Janice scored a 1410 on her SAT. Mikey scored a 960. Find their z-score. So remember that z-scores can always be calculated by using the formula x minus mu divided by sigma. And we know all of these components. So for Janice, remember x is the score in question. Janice had a score of 1410. If we subtract the mean, 1060, this gives us basically how much higher than the mean she got, which is 350, and take a ratio to the standard deviation. Janice's z-score will be exactly 1.75. And Mikey's is a little bit under the mean, so we'd expect it to be negative z-score. In fact, he's negative 100 under the mean, which would give us a z-score of negative 0.5. And remember, the whole point of a z-score is to tell us how many standard deviations is the score away from the mean. Like with Janice's 1410, she's further away from the mean, which is in the center, than Mikey was with his 960. And it tells us, well, Mikey's about half a standard deviation, or exactly half a standard deviation below the mean, whereas Janice is almost 2 standard deviations past the average, as a sense of, again, that's the point of a z-score. How good is our score? Now, to actually determine percentages, that's where we need to go to a z-table. So like for part E, it asks us to determine what percent of students scored in between these z-scores. But basically, we want to look up those particular values in a z-table. So negative 0.5 and 1.75. So let's just go to ztable.com, or again, you could use your table A in your book or whatever. But 1.75 has a z-score of, or this 1.75 is the z-score that has a cumulative probability of 0.9599. So let me just go ahead and write that down. And again, what I recommend, as in class time, I was saying, well, it helps to draw a graph representative of that z-score, because again, 1.75 is going to be much past the first standard deviation of the mean, and the cumulative probability, we'd expect that to be a lot, because cumulative probabilities are always the left hand area of these graphs representing a percentage of the population that fits the certain paradigm, and most people are going to have a z-score smaller than 1.75, and in fact we now know that it is again, going back to 1.75, about 96% of the population, 95.99%, will have a smaller z-score than that amount. And we also need to figure out the cumulative probability for Mikey's z-score, which was 960, and he had a z-score of negative 0.5, or his actual score was 960, his z-score was negative 0.5. So going to our z-table, negative 0.50 is right here. 30% of people will have a lesser score than Mikey. Again, that's kind of what that means. Negative, so that would be 0.3085. And that's, actually, I'll put this a little bit over here because 0.5 isn't even a full standard deviation below, but basically 30% of people are less than Mikey's. And what we want to know is how many, what percent of students scored in between a score of negative 0.5 and 1.75 are in here. Or as, you know, again, as I said in class, it's the difference between the cumulative probabilities of each. You basically just take the difference between those two. You take this probability minus this probability. That will give us the probability we care about, the percent of students in between those two z-scores. And if we go ahead and do that, 0.9599 minus 0.3085, that would leave us with 0.6514, or, you know, approximately 65.1% of students had a z-score, scored in between a 960 and a 1410 on their SAT. And looking at question F, this is kind of more what we've been working on in chapter 15 and 16. But if we took a sample consisting of 4,000 students, we could then ask how many of them scored in there. Well, we could just multiply that percentage by our sample, and we could get a sample amount for how many students actually had a particular score.